So in this example, I'm going to be talking a little bit about the most basic example of a genetic algorithm, which is to create a vase or an object that has as large of a volume as possible with using while having as least of a surface area as possible. And you can imagine that this could roughly translate into the question of how do you make an object that uses as little material as possible but can contain a lot. And just to give you a little sneak peek of what this does, this is using Galapagos, which is built into Grasshopper, and trying to maximize volume, minimize surface, or in other words, if you can divide volume by surface and get a number, it's trying to maximize that number. And it uses the solver to iterate all these different versions, between all these different versions, to kind of find an example in which the volume divided by the surface, that number is the best. So just based on that singular number, it's iterating between all of these different possibilities. And through the process of the genetic algorithm, or by a kind of simulated evolution, it's giving us the best example. So here's an example of one form that it thinks is an ideal best. And just to run through the process of evolution, or the genetic algorithm, evolution, or the model of evolution that the genetic algorithm uses, is that it starts out with an initial random population. It reproduces them and creates mutated offspring with variation in different characteristics. And then it competes those offspring against each other, or it selects only the best out of them. So it competes within that offspring. And then it selects the best one that then become the next generation. And then that next generation then reproduces again, creating more offspring with more variation. They compete, or you undergo this process of the survival of the fittest, and then create a new generation. And then that continues onwards. And when you undergo that process, you end up with versions of specimens or that have been evolved, so to speak, to be better or more fitter. That process of evolution. And so the question really is of what does fittest mean? That's kind of a really important question, especially when we're talking about the genetic algorithm. So I'll go into a little bit of detail in this example, and the other two examples will show you a little bit more about how you can mobilize this concept of what is fittest or what is ideal to come up with many different kind of interesting possibilities that can augment or help your tool. So I'm going to start from scratch here, but I'm going to borrow some elements from our former example. It's just the portion of the interface that lets me sync up these two views. You should have seen this many times before. So I know it's not really necessary in this example, but I'm going to use it because I think it's a pretty important default to have when we're designing our tools. So what I want to do is I want to create a vase, let's say, or some sort of object, and I want the volume to be as large as possible and the surface area to be as small as possible. Now, just within the scope of this example, I'm going to use a model of what a vase is in order to do that. And just within this example, I'm going to have 3 lines like this, like so. And then the center line is going to change and be scaled. And depending on how it's being scaled, these 3 lines will be lofted together and will create a vase. That's just my model, my internal model of how I want the vase to be, and then Galapagos, or the genetic algorithm, then steps in to solve that. So there's very much a human or a designed element of what kind of object I want, and then Galapagos solves for that. So first of all, I'm going to design the system for our base. I'm going to use a geometry pipeline just to grab this line. You could not necessarily have to do that, but I'm just going to. You could draw the lines yourself, but I'm just going to drive it off of geometry pipeline because again, that's another helpful way to turn this process into a tool and not use the grasshopper set one multiple geometries function. So I'm just going to really quickly make what we think is our vase. I'm going to move this geometry upwards in the z direction by 10 units, say, or perhaps 20 units. I'm also going to move it up twice that amount. And I'm also going to scale the object in the middle. And it requires the center, so I'm going to get the area of that object. So I'm going to scale this object around this point by a factor of, say, 0 to 10. And I'm going to grab this geometry, the bottommost ring, the middlemost ring, and the topmost ring, and then I'm going to loft it together. I'm going to set the minimum to be 0.1 just so that we're not scaling the vase infinitely small. And since lofted this is hollow, I'm going to cap this object. And there we have our vase. And I'm just going to hide everything just to make it a little cleaner. So now we have our vase. And just to get into the habit of making things pretty, I'm going to use a custom preview object and a swatch object. Great. So now we have our object, our vase, and it's driven. We only really want to change this, and we want to say have the vase or the object have the most volume and the least amount of surface area. And so we can take this object and analyze the volume of it. We can also analyze the surface area of it. And so you can see that when I change the slider, both the volume and the surface area change. Now, I'm actually going to use the text tag, and actually text tag 3D. I'm actually going to represent it, this information in space. So I'm going to run through this really quickly. What I'm going to do is I'm going to write a little template. I'm going to say volume equals vol area equals $area in all caps, volume divided by area equals vol area. Now the dollar signs are actually just a convention. It's just an internal symbol that I'm later going to replace in. And the dollar sign convention is something that is sometimes used in certain kinds of computer code, which is why I'm using it here. It could be anything. It could be XXX, it could be ABC. But the reason I'm doing this, you'll see, is because this can become a handy template for a way in which I can manipulate text. I'm going to use a replace text function. And so I'm going to replace this text, find a fragment. So this is where this comes in. I'm going to replace the vol fragment with this volume. And so the output of that is going to be, you can see where vol was, 822.43 was inserted. I'm actually going to do the same thing on this, but instead of vol, I'm going to replace area, and I'll replace it with this object, their corresponding symbols. So you can also see that area equals 771.88. And then I can do it again so that I can get the volume divided by the area. Volume divided by the area. And I'll plug that in to the result, or to the text to replace with. And I'll make sure to change the thing I'm replacing is vol area, because there was vol area up here. So if I do that, then it looks like it's not quite working. Oh, I see. This is not quite working because when it's replacing vol, it's replacing both of these vols. I'm going to call this VA, let's say. Great, so you can see this is what happens. And this is convenient because maybe I want to change this and say surface area. I can just change this text, and this text will be replaced accordingly. So that's great. And since this is helpful but not really important, I'm going to grab this and make this into a cluster. So this is kind of all encapsulated and plugged in there. So great. So now I have this text. I'm going to plug that into the text location. I need to put it somewhere. I could put it in the middle of this, but that way I probably wouldn't be able to see it. So I'm going to grab that center point, just right here, and then I'm going to move it upwards in the z direction. And then locate the text there. In fact, it looks like the text could be a little bit higher. Great. Hide that. And I'll use the swatch to color that as well. Great, so now I have this representation. Now, I didn't address this as well, but right now I've divided the volume by the surface. Well, why is that? It's because when you do the genetic algorithm, you're trying to improve a single number, in this case using Galapagos. Now, there are other ways to use multiple different numbers, and we can get into that later. It's called multi-objective optimization. But using a singular number is, for our purposes right now, pretty helpful, and just using that you can do a lot. And so if we're trying to improve a single number, in this case, if we want to have the volume be as large as possible and the surface be as small as possible, if you divide the volume by the surface, then if the first surface goes down, the volume, this number goes up. So this is a way that we can incorporate both the argument of the volume going up and the surface going down into a single number. So I'm going to use the number component to hold this. This is our fitness function. That's a term used in genetic algorithms to determine the function or the kind of way in which the mathematical calculation that determines what is more fit. And so we're saying the higher this number, the more fit you are, or the vase is. So now I'm going to use Galapagos, which I can do by typing in Galapagos. And again, this is included in all Grasshopper installations. And so the fitness function is this, and if I carry this out, you can notice that I'm getting a green line. I don't actually plug it into the output or input. I have to drag it from the Galapagos into a number, and that just means it's kind of watching that. And as for the genome, to continue the genetic metaphor or analogy, is that the initial population, or the initial all sorts of specimens can be defined as a result of some sort of DNA or chromosome or genome, which is kind of the underlying gene sequence or the underlying data that then gets manifested into an organism and then expressed. In other words, it's the data that affects the geometry that the genome, what the genome is, or the data that it affects anything. So in this case, we can use multiple numbers, but we're just going to plug in or do the same thing and listen to the factor. So it's only going to control the factor, and it's only going to listen to the fitness function. Now, if you double-click on the Galapagos Editor, you see this window, and this is kind of a little introduction that's helpful to read. And on the left-hand side, you get a series of options. And the most important one is this one, fitness, minimize, maximize. And so in this case, we want to maximize that number. The threshold is above what you want to see. So if you're okay with having a volume divided by surface area ratio of 2, then you set it to 2. A limit is how long you want it to go. So if you can say, okay, don't go longer than an hour and 30 minutes. The thing about genetic algorithms is that they can go on forever. And then you have all this other aspects, which are pretty interesting and helpful, but I'm actually going to go into detail about them in the next video. But they kind of pertain to how much randomness you get, or how many mutations you get between different types, or those kind of things. And so I'm going to click on Solver and stay on the left-hand side. You can see this little diagram of sperm entering an ovum, an egg. And so I'm going to just start the solver. And as it's going, you can see it's kind of stopped. The reason why that is because I'm on this mode that only displays the better genomes. So this is the window in which all action happens. So if I hold on this, it'll just show me the better ones and the better ones. This will not show, this button on the right will not show anything whatsoever, or it will just stay there, do not display any genomes. I believe it can make it a little bit faster. But because we want to see what's going on, we're going to click on display all genomes. And that's just going to iterate between all the different possibilities, whether or not they're the best or not. And then over here, you see this window. On the bottom right-hand side, this is giving us the fitness function of which one is the best. And I believe this is its variance or its percentile ranking within all the other possibilities, answers. This window, and it's a little hard to understand because we don't have multiple genomes or multiple inputs, but it's a graph of the different kinds of factors or numbers, and the more they overlap, the darker they get. This will be easier to see when we have a different kind of genome, and you have multiple values, and it kind of looks like a zigzagging line. The window down below on the left-hand side is a representation of the types of values, and they're kind of organized in 2D in space, roughly to illustrate how similar these options are. Now again, since we're operating with a single value, it's a little bit harder to understand, but if you use many different values, it'll start to clump these clusters together. So if you're running this and you see 4 distinct clusters, it means that the evolutionary solver has sort of determined that there are 4 different types or 4 different families, distinct families. Now the fact that they're all kind of clustered together means that there's kind of one general similar kind of family. It doesn't mean that much in this scenario, especially because we're dealing with one factor. And the dots are the dots from the previous generation that were used to mutate and make new ones, and the X's are the least fittest ones which were not used. Finally, this graph up above, on top, is showing you, this is the line of, if we zoom in, this is the line of, I believe, the average, or sorry, not I believe, it is the average of all genomes, and it's the best, most performing line, and these bands are each standard deviation, which if I recall is 36%, or a standard deviation away of how disparate or disperse the values are. So, in other words, this is the highest, most fitness function in generation number 7. This is the first standard deviation worth of individuals and how well they fared, and this is the second deviation. So the more spread out this is, the more variance your generation had, the more tighter it is, like over here. It means that all of the specimens or all of the tests had a pretty similar example or number, and they kind of constantly fluctuate. Now it's not necessarily that as you go on you get the best answer, because for over here, number 4, you see you have a pretty good answer or solution, while as you go later, you even get worse solutions within the generation. So you might come up with a good solution early, you might come up with a good solution later, but normally you'll watch the kind of bands narrow, or this kind of width narrow up as the genetic algorithms tries to find more and more of a solution. Now, the reason why it not necessarily do that is that the genetic algorithm also kind of inserts random versions also, because in the process of trying to simulate evolution, you also want to have many different kinds of mutations, not only those that occur between competing the fittest together, but also those that happen from just kind of new factors. And you can actually accelerate that aspect by clicking on this button. You add additional mutations, so the next generation around will probably be super disperse, I believe. And then you'll see a lot of different possibilities. Now, again, since we're dealing with one singular factor, it's like a very simple example, so the graph is a little bit less helpful. But you'll see in the other videos that when we're dealing with, say, 10 factors, or 100 factors, or 100 input genome, then this diagram becomes a lot more helpful. So again, over here are the kind of list of possibilities, or the list of winning specimens. So we're actually going to stop this because it can go on forever, and we've already done 40 generations. And I'm going to get the topmost one and reinstate it. And what that reinstating means is that it's implemented it within Rhino. If you click OK, this is what we get. And incredibly enough, this has a volume to surface area of 7.3. Now, this is surprising. I was actually honestly expecting to get a more spherical shape, but that's what it is. So that's interesting no matter what. And that has determined that for the time being, that's the best way into getting that ideal ratio between volume and surface area. This has a lot of volume and relatively little surface area for you, so you get a lot more space per material, let's say. You know, we can also try it with like a larger bottom surface, or you know, we can make kind of an arbitrary form, and we can try that out again, see what we get if we maximize that number again. I'll iterate through the possibilities. And I'm going to zip forward and skip a lot of the evolutionary process for those who are watching. Okay, so I've iterated through 38 generations. And oh yeah, one thing to show is that you can notice that the slider being controlled by Galapagos is running through many different possibilities down here. So I'm going to stop the solver and then reinstate the most ideal version. And that's this, which is interesting. When the base was a circle, then our form was really large, and the base is this polygonal form. You get a slightly smaller object, but it's clear that this too has also been solved to have maximum value, minimum surface area. And it's a little harder to see, but I'm going to move my text up. You can see that that this, depending on the bottommost surface, the overall form of the vase changes. So this is a kind of canonical example, and solving this process wouldn't be very easy. Or you could do it by a human. You could move the slider gradually until you found a point at which it seemed to be the maximum. Now, this is an example that's very easy to solve because we're working with one slider. But once you start getting into multiple sliders or other different kind of challenges, then the possibilities or the problem gets vastly more difficult. So the next two examples I show will be a little bit of an example in how to use Galapagos to solve harder or not so easily understandable or easily solvable problems.